Hello mathematicians, just a little flashback to some of your Extension 1 ideas. So when we're drawing these graphs, which are often going to be things that require as much of an art as a science of graphing, look for all of these little extra bits. So are there any restrictions on the domain? And likewise on the range. Consider the limits as you go a long way to the right or a long way to the left on our graph, so plus and minus infinity. Is the curve odd or even? Sometimes that can help with the sketch. Most curves, of course, are neither. Can we find the intercepts with the axes? And particularly the intercepts with the y-axis should be okay. We might want to find the first and second differential if that's within our realm of ease to get the turning points and determine their nature. There are also some little bits about limits which are on the edges of the Extension 1 course, but you might think about those. So for example, this graph opposite compares for varying values of x the curves of e to the x, x squared, x and log x. And we can see that for large values of x, the order in which, their order of magnitude basically. So if we have one of these functions divided by one lower down, then as we tend towards infinity for the x value, we will tend towards 0. So log of x, for example, being divided by x squared, a bigger number. I don't know whether I said that around the right way a moment ago. But the smaller number divided by an ever increasingly bigger number, that will tend towards 0. Whereas if we have a big number divided by an ever smaller number, that will tend towards infinity. If we look quickly at these and determine the limits as we go to, I'll just do plus infinity for the sake of brevity. So x to the fourth plus 1, and what I would need to write, which I'll only do for the first one, is that the limit as x tends to infinity of x to the 4 plus 1. Now we can see that if we're going to raise infinity to the fourth power and add 1, we're pretty much going to still be at infinity. If we have e to the minus x, if we think about that curve, the curve itself goes that way. So as we tend to positive infinity, this curve tends towards 0. So again, if I wrote it out fully, the limit as x tends to infinity of e to the minus x is 0. E to the x squared, well, if we think about that curve, that will be always e to some positive number, and e to a positive number is always going to drift up that way. But that's about all we need to know. The main thing is that we're going to tend towards infinity. For this one here, so this would be more like Extension 1 material. If that's what y is, then we could rewrite that y by dividing every term by x. So the top line will become 1 and 1 and 1 on x. So we want the limit as x tends to infinity of this. So this term will head to 0, so that will just be 1. For our next one, if we divide every term by the highest power of x, which is x squared, then we're looking to take the limit as x tends to infinity of 1 on x over 1 plus 4 on x squared. And as x tends to infinity, this tends to 0, and that's the main bit, so our answer is 0. Now for our next little bit, sort of on the edges of Extension 1, so it might be useful for more difficult questions. So if we have one function divided by another one, if the degree of the bottom is greater than the degree of the top, then we're going to basically have some x's on the bottom. So as x tends to infinity, then y will tend towards 0 because we'll be dividing by an ever bigger number. So the x-axis is an asymptote. So there's an example here of that. which you could check for yourself by dividing every term by x squared if you wish. If the degree of the the numerator and the denominator are the same, then as x tends to infinity, y will tend towards some constant value. So we're going to find that we have a horizontal asymptote. So if we look at this example here, same degree, and there's a horizontal asymptote at, well, there's a vertical asymptote at 1, and there's a horizontal asymptote which is at 1 as well. A common technique for finding that horizontal asymptote is to look at your function and see if you can write it in what we'll learn later on are called partial fractions. We'll just call it for the moment a rearrangement of the fraction. So if I rearrange this fraction to get a constant plus a fraction, then I could write it as x minus 1 plus 2. So that gives me x plus 1, I'm just rewriting as x minus 1 plus 2, putting that all over x minus 1, breaking that up, so I've got x minus 1 over x minus 1, which is 1, plus 2 over x minus 1. So this is then the same thing as that. And you can see that as x tends to infinity, this term will tend towards 0. So y equals 1 is the horizontal asymptote. Now lastly, if the degree of the the denominator is less than the numerator, then because we'll have x's on top, then as x tends to infinity, y should tend to infinity as well, depending on the sign. But long division may yield an oblique asymptote. So our technique of long division from polynomials may show us that we actually have an oblique asymptote. So for example, for this curve here, y equals x squared over x minus 1, if we took our x minus 1, divided it into x squared, then this would go into this once, so that will give us x squared minus, go into it x, so that will give us x squared minus x, so that will leave us with an x there. So we could rewrite x squared over x minus 1 as the product of x plus x over x minus 1. So as we shoot off to infinity, this will go to infinity, but this is going to be the governing asymptote. So we've got y equals x sitting up there, guiding our journey off to infinity, if you like.